Okay, calculus class, we're going to continue our way through Unit 1. I split those into two sections just because the second half seems to be very different than the first half, where we're focusing on continuity now instead of limits. We still use limits, but more focused on just determining continuity and different things like that. So, two sections, or two essentially chapters from Unit 1. So we're going to start talking about this idea of discontinuity. And real quick, if you had to sketch a graph that is continuous, what would you draw? Probably some of you, get your axis ready, and then maybe some of you just draw a line. That is a continuous function. Some of you might put some fancy little curves in it, and that's also a continuous function. There are lots of different things you could do. More importantly, how would you sketch a graph that is not continuous? Okay, a little hint I have for you there is that there are 3 different ways. Some books claim 4, ours only claims 3, and 3 is most common. So what might we have if we have 3 different types of not continuous functions? Well, one thing that we've been taught in previous courses is sometimes functions have holes. So we might have this function that looks like a line but has a little hole in it. Okay, there's something like that. We might have a function, our rational functions have sorts of asymptotes going on. Not sure what those things look like, but we could have asymptotes. And the third one you've seen quite a bit in the last half of the chapter when we were talking about limits. We would have, one function or part of a function that comes up here to a hole, and then maybe this one is a closed circle and it does something else. Okay, so the 3 types of not continuous or discontinuous things are holes here in pink, asymptotes here in purple, and jumps. These are called jump discontinuities in that turquoisey color. Okay, here's better, more technical definition of what's going on in those things. Okay, so very informally, a continuous graph or function has no holes, jumps, or gaps. Okay, you can destroy continuity in these 3 ways. This first graph, number 1 down here, corresponds to the first graph where just f of c is not defined, so that means there's a hole. Okay, that was the hole. The limit does not exist, but the function does. Okay, so that's kind of this jump here. And then the other thing was the limit exists but is not equal to f of c. So we have different things going on here. None of them were an asymptote, but that is one of the types of discontinuities that we will focus on later. This section does focus on holes and jumps. Okay, here a little more formally, because it is calculus and you should see formal definitions. Here is the formal definition of continuity for calculus. Okay, and notice it says continuity at a point. Most of the time you're going to look at a function and it's going to say determine whether it's continuous at a specific point, or you will know enough about the function where you can just determine what point you need to check out. So there's always 3 things. You have to see that f of c is defined, the limit as x approaches c of f of x exists, and those 2 things have to be equal. Okay, if we want to extend that definition to an open interval, then we have basically the need to check every single point in the interval. But like I said, knowing what we know about functions, that sounds way worse than it is. Okay, the note on the bottom there, you probably already read it. Yes, this is important. like super duper important. Yes, you have to know it for the rest of the year, and at any time you have to tell me the 3 rules for continuity, and you will have to use it to prove continuity at times, including an AP Calc exam. All right, types of discontinuities here. Discontinuities can either be removable or non-removable. The non-removable ones are our jumps and our asymptotes. The removable ones, then, the line disappeared, are the holes. Okay, they can be removed, so to speak, by just factoring typically and canceling that out. So we could fill in the holes. Okay, and that's what I said down there. So let's talk about the continuity of each function, because I said it wasn't so bad, right? Most of the time you're going to be able to use your really intelligent brains and just tell me where something is discontinuous. And you may even know whether it's a hole or an asymptote at any given time. So let's look at this first one. F of x is 1 over x plus 1. Functions are continuous unless there's a division by 0 or radicals of negative quantities, even radicals. So right now we have to be concerned about something in the denominator that's going to cause a division by 0. All of you can see that a negative 1 is going to make that 0, and there's nothing to cancel on top. So continuity, there's some sort of discontinuity, and being we're smart, we know it's a vertical asymptote at x equals negative 1. Okay, you could just say discontinuous at x equals 1, but the more specific you can be in the case of continuity, the better. Second one, g of x here, x squared minus 16 over x minus 4. So we know that the denominator is going to be 0 when x equals 4. So it's discontinuous at x equals 4. But what kind of discontinuity is that? Well, knowing what we know about functions again, our numerator is factorable as difference of squares, so x plus 4, x minus 4. And when those two things cancel out like the x minus 4's do, that's how we know it is a removable discontinuity or a hole. In calculus, we do call them removable discontinuities, so get used to kind of changing your vocabulary a little bit. Okay, what about h of x down here? Cosine x. Is there a radical? No. Is there division? No. Is cosine x continuous all the time? Yes. So we can say continuous. That's not how you spell continuous. At all values of x. Or if you want to get real fancy, when x is an element of the real numbers. So anytime x is a real number, we have a continuous function with cosine, just knowing what it looks like. Okay, here's another function, couple functions actually. The first one, f of x, we have a piecewise function, and looking at x plus 3, that's a line. It's continuous everywhere on its domain. X squared plus 3, also continuous everywhere. So our main concern is what's happening at 0. That where those two things might separate, they also might connect. So we have to check the continuity at 0. And remember, there's 3 things that have to happen. F of c has to be defined. Your limit as x approaches c of the function has to exist, and those two numbers have to be equal to each other. So let's check it out. Can I find f of 0? Yes I can. This part of the function, the top branch, tells me that when x is equal to 0, I plug it in, and I'm going to get a value of 3, because 0 plus 3 is 3. The next part tells me I have to examine the limit as x approaches 0. Now it's piecewise, so I have to look at from the left and from the right. Okay, so when I do that, I get limit from the left. I'm using the top branch, so I plug in 0 there and I get 3. And then limit from the right, I use the bottom branch and I plug in 0 there, knowing it's an open circle, but limits can be open circles. Plug it in there and I also get 3. So I know that because these two are the same, the limit as x approaches 0 of f of x is 3. Now because limit as x approaches 0, f of x is equal to f of 0. Because this is true, well, we had our first thing there, our second item there, and our third there. Now we can say, therefore, f of x is continuous. Super fun, right? What about the cotangent function? Is cotangent like cosine, where it's just continuous everywhere? Not so lucky there. Cotangent is the cosine function over the sine function, right? So we do have division, and it's repeated every pi units because that's the domain of cotangent. So we need to figure out where sine is 0. That's when we're going to have some discontinuities. So sine is 0 at 0. It's also 0 at pi and 2 pi. And if we continue, it's at another pi and another pi and another pi. So we would want to say that h of x, and the way you say this is can be different. You just have to get your point across. H of x is discontinuous at all x is pi times n. So all multiples of pi is what I'm saying, and we want to say n is an integer. This is going to be probably new notation for you. So this part up here says that we're doing multiples of pi, and I saw that by just my investigation, knowing what sine does. And this part says I can use any n value, positive or negative, as long as it's an integer. So the -3, -2, -1, 0, 1, 2, those things. Okay, that's new notation, and it's going to be a little tricky at first, but make sure you keep asking questions until you really understand that, because you're going to see it quite a bit this year. Okay, a couple more. Maybe you should try this one on your own and pause the video and check the completed answers when you are done. See if you can figure out continuity on your own. That would be a great idea. Okay, and try that one as well. So try these last two. I will upload a completed document so you can check your work, but it would be really awesome if you could check this out. Let me know if you have any questions. Have a good day.